Okay, welcome everyone. Today is my big pleasure to introduce Alicia Dickenstein from Argentina, from the University of Buenos Aires. And Alicia will speak about her joint work with Sandra De Roca and Ralph Morrison about iterated and mixed discriminants.
Okay, thank you, Vanya. Okay, so as you said, this is the title and these are my co-authors, and this is our palindromic date. So, so how did people classically study the intersection of two quadrics in free space? No? But if you have two generic quadrics in three-dimensional space, they will intersect in general a non-singular quartic curve, right? But it might happen that the intersection is a reducible curve, or it's not reducible, but it has a singular point. So the idea was how to characterize when is it that the intersection of these two quadrics gives you a singular quartic curve. And this was studied classically by Bromwich, Salmon, and also in a computer-aided geometric design. This was studied around 1989. And then, so what did they do to describe this singular intersection of quadric surfaces? F0 and F1. So each quadric, you can write it in this way. This is X is the vector 1, X1, X2, X3, and this is a 4x4 symmetric matrix MI. And essentially the entries of F are the coefficients of F up to a factor of 1/2 in some cases are just the coefficients of this matrix M. Then what they did, they considered a pencil, I mean the line going through F0 and F1, and they computed the determinant of the corresponding matrices. And then you get as this a polynomial in this variable lambda. So you have this polynomial which has degree 4 because these are 4x4 matrices, and then they try to detect for which quadrics, this means for which matrices this polynomial has a multiple root. And then they classified the singular intersection studying this question, and they use something which is called the Segre characteristic, which is based on the Jordan normal form of the matrices. And then there were similar methods. Schleffly used this to study hyperdeterminants, that is multilinear polynomials. This was way before in the 19th century, but this was published in 1953. And then similar thing as we saw in geometric modeling, they were classifying what are called Darboux cyclides. This is also very classical stuff. These are polynomials of this form. This is linear, and this is quadratic, and this is degree 4. But in fact, these surfaces, Coolidge proved that they are the projection into 3 space of intersection of 2 quadrics in 4 space. And they were also studied in the framework of geometric modeling. And we saw a recent article about this. And so the question is, why does this work and what is behind these methods, how to extend it? And of course, the key word is discriminant that we saw in the title. So assume you all know what is a univariate discriminant. So how a degree of a polynomial of degree 2 is, in fact, it is not a function of one polynomial, but is something which is attached to the family of all polynomials of degree 2 in one variable. So it's a family of polynomials, and the parameters are A, B, C, which are these coefficients. And then given a particular F has a double root if and only if the discriminant, which is, we will say at the same time, it's a function of F or a function of the vector of coefficients ABC, is this our beloved b squared minus 4ac. Okay, this is the condition. And similarly, this is also quite classical. For any degree in one polynomials of any degree in one variables, there is an irreducible polynomial in the vector of coefficients of f c0 cn, which has, it's a polynomial in the coefficients of degree 2 times n minus 1, which vanishes whenever not all the roots are simple. This means there is a common root of f and its derivative. And it's defined up to sign if we ask that it has content 1. So ways of computing the discriminant, in this case, of the discriminant of a polynomial of degree 2 in one variable, there is probably, you all know that you can use resultants. So this is the resultant of two polynomials would vanish whenever they have a common root, except that if we do this naively, this is the Sylvester matrix, we're going to get here this A, which seems to be naive, but in fact it comes from the support set is 0, 1, 2, okay, and the convex hull is the interval 0, 2, and 2 is in the boundary. In fact, in more variables, there are boundary components that occur is less naive than these. In general, people in one variable just put monic polynomials and they forget about this extra factor. But in general, you get extra factors. Or you can homogenize your polynomial, and in this case, get an exact formula. And then by Euler, we have this equality. So the vanishing of f and one partial is equivalent to the vanishing of both partials. Both partials are linear homogeneous functions of x and y, and then we have a common root when the determinant of their coefficients is equal to 0, and this is precisely what we want to get, plus or minus this. And in this case, there is also an obvious way of doing this. If a is non-zero, we solve f prime equal to 0, and we get t has to be minus v over 2a. Then we replace this into f, and then we clear the denominator, and we'll also get the discriminant. More in general, we will need to use elimination of variables with an elimination order in a computer algebra system. So this is kind of naive and easy in this case, but then it is extended, but it is more involved. So what happens with a quadric in n variables? Okay, quadric in n variables, we can homogenize it again, and then we write f as x times this matrix times x transpose. And then if it has the hypersurface f equals 0 has a singular point if there is a non-trivial common solution again of the partials, and happens precisely when the determinant of this matrix is 0. So the discriminant, which is the condition under which this, is the closure of the condition under which it has a singular point, is given by the determinant of this matrix up to integer factors, up to an in general. So if we do this, for instance, for in the plane, we're going to get a factor 2. So in fact, what they were doing, they were computing discriminants when they were computing the determinants of the matrices of the quadrics. So in general, what is an A-discriminant? These were defined and studied by Gelfand, Kapranov, and Zelevinsky in a book, which is like a Bible, 89 Birkhäuser Green Book. So the setting is you fix a finite set of lattice points. They don't need to be non-negative, it's the same work. And then you get a family of polynomials with support A. So f is identified with a vector of coefficients. Here I put C because of lack of space, but we could put here any other algebraically closed field of characteristic 0. And maybe you don't need this for everything, but I will, as I'm going to take tangents, I need a characteristic 0. So the A-discriminant is the unique up to sign irreducible polynomial called dA with integer coefficients. And up to sign, if we assume that the GCD of the coefficients is 1, but there are also some arithmetic details that I am misregarding. I'm looking at them in a geometric way, but for number theorists, this number matter a lot. It's a polynomial with integer coefficients in the unknowns, which unknowns are the coefficients, which vanishes wherever has a multiple root in the torus, because as we are getting integer exponents, we can only, in principle, evaluate this as a point with non-zero coordinate. So this is the closure of coefficients of which there is a point in the torus where f and the partials vanish. Whenever this is a codimensional condition in the family of such polynomials. Okay? Otherwise, we don't get one equation. If this is not the case, we usually say that dA is equal to 1, but we are going to work in the case where this is a hypersurface, and this is what is expected in general. But what happens is a different way of looking at this is considering what's called the XA, which is an associated projective toric variety. So we order in some way the exponents A, and we send a point T in the torus to, let's say that we order, we number A like coefficients A0 up to AN. So we send T to the A0, to the A1, to the T to the AN. And then the closure of those, of the image is this variety XA. It will lie in P raised to the number of points to the cardinality of A minus 1. And this XA has a dual variety. The dual variety are the hyperplanes that intersect XA in a tangential way. And this is equivalent, so any F can be identified with a hyperplane section on XA, and this is the condition that the intersection is contained in the tangent space. So the tangent that the hypersurface contains the tangent space at the point of intersection. So let me tell you what is in a naive way what is a mixed discriminant. So here A will be the vertices of the unit square. Then a polynomial with these exponents is just has this form, is coefficient plus something times x plus something times y plus a coefficient times x y. And here I have two different pairs of polynomials with support A. One is the blue hyperbola with this equation, and this is the red hyperbola with this other equation. And here I have two different hyperbolas. You see, in general, we have degree 2 polynomials, but we don't have the highest terms. So in general, they won't have 4 points of intersection, but generically there will be 2 points of intersection. And these 2 points of intersections will be in general transversal, so the tangents are different. So we get 2 different points where the intersection is transverse. But it might happen that we get a single point where the tangent line coincides. Okay, so the mixed discriminant will vanish at those vectors of pairs of polynomials of pair of vectors of coefficients for which this is happening. So given f and f1 to such hyperbolas, the mixed discriminant, then I'm using a little bit different notation, is it's called the hyperdeterminant of format 2 times 2 times 2. So if we evaluate this polynomial at 3, 1, minus 3, minus 2, 1, 1, minus 3, minus 2, we are going to get 0 because the intersection is tangent. And then this mixed discriminant can also be computed similarly via a pencil. And this was studied by Schlefly. Okay, so I need to go in the other direction. So with some mixed discriminant in general. So I'm sorry, but my mouse, okay. So again, our data is going to be a finite set in Zn. And then I have another input, which is a number r greater or equal than 0, an integer greater or equal than 0. And so we take r plus 1 Laurent polynomials F0 of r with support A and coefficients in an algebraically closed field of characteristic 0. We have said each f is going to be identified with a vector of coefficients again. So the mixed discriminant is a polynomial in all these entries, which will vanish if there is a non-transverse intersection. But when this condition is 1, using a result by Nick Katz of left-shot pencils, we prove, it's not difficult to prove, that it is enough to consider not only non-transverse, but non-degenerate non-transverse. For instance, they are the, so they share the same tangent, by the Hessian has maximal rank. Okay? And then if we take R equals 0, we recover the definition of discriminant that we had a second ago. Again, we can assume that the singular point is the closure of coefficients for which there is a singular point which is non-degenerate. And also these mixed discriminants as well as resultant hyperdeterminants are all special cases of these A-discriminants that I just told you about via what's called the Cayley trick. Okay. And what is an iterated discriminant? Okay. Again, the input is A, which is the exponents of the polynomials in my family, this integer R. And I need to assume that A is non-defective. This means that the codimension of the dual variety is 1. So we have this equation dA, which has some positive degree that I'm going to call delta. And then we need that R to have a non-trivial answer, that R is at most the dimension of this projective variety XA, which equals the affine dimension of A. So we take the convex hull of A is the dimension of this object. It's not the linear dimension, it's the affine dimension. Then here I skip the R. So we have F0 FR which support A with corresponding vector of coefficients. And then we're going to take again this linear combination with, I add new parameters lambda 0 and lambda R, and we consider this combination. So this, if F depended on, let's say, on variables x1, xn, now have this depends on lambdas and the x's, and two sets of variables. So what we're going to do, and also the F, we see them as the F's, we see them as polynomials in this family where varying coefficients. Okay, so we have the X are the variables, C's are the coefficients, and lambda are these new parameters. Then we think of lambda as parameters, and we consider the discriminant of these polynomials. So we fix the lambdas. Sorry, we fix the coefficients. We move the lambdas. And for each choice of the coefficients, we consider the discriminant of f lambda, and we'll get a polynomial in lambda of degree delta that in general parametrically will have coefficients here. And then one particular case of these A-discriminants is when we take the family of polynomials of degree delta in for instance, in R+1 homogeneous variables. So this means that we have delta, dilate, delta 1 is the unit simplex in this dimension, and we take the delta dilate, and in fact, we are going to take all integer points there. So associated to polynomials of degree delta in R+1 homogeneous variables, there is an associated A-discriminant which coincides with also a classical more classical homogeneous discriminant, and there is nice work by Bousset and Jean Leloup on this projective approach. And then we define the iterated discriminant this way. So this, we fix the coefficients. We think of this, we consider the discriminant of f lambda. This gives you a polynomial in lambda. And then we take the discriminant of this polynomial in lambda. So dA eliminates the x variables, gives a condition on the coefficients, and d delta eliminates the lambda variables. So we end with a polynomial which only depends on the coefficients, or that is on the original f's. And when R is bigger than the dimension of XA, we just define the iterated discriminant equal to 0. So let me say it again. We have the f's, which have coefficient C's and depends on variable X's. We form this. We take the discriminant of this polynomial, which will give us a polynomial in lambdas with coefficients here. And then when we do this new elimination, we eliminate the lambda variables and we get the condition under which this polynomial had a double root in lambda. And then this is our definition of iterated discriminant. So what were these classical computation about? Well, they were trying to compute a mixed discriminant, but instead, so they wanted to understand when is it that two quadrics would have a non-transverse intersection. This is given by a mixed discriminant, but instead they were computing an iterated discriminant. So they consider the two quadric surfaces represented by the matrices, and they computed this way the determinant of the matrix and then the discriminant of the polynomial in the univariate polynomial that they got. And what is interesting is this gives a compact way of computing the mixed discriminant. This one is a little bit misleading. One means that you have two because we have r plus one. So this is r. So this means that we have two polynomials. And what is interesting is this: if you try to expand this expression in terms of the coefficients of M2, this is beyond, at least 2 years ago, beyond the capabilities of Macaulay 2. It's huge because think that the general it's a polynomial on the coefficients of degree 12 in the coefficients of F0 and 12 in the coefficients of F1. And a general polynomial of this by degree has those many monomials. It's really huge. So we have an easy and compact way of computing this interesting object. Okay, so let's try to generalize. Let me show you two examples. One is what's called we call it the it's not that I call it, it's called like this, the Hirzebruch surface F1. So A is the following. There are these 5 points displayed here. And then we consider a family of polynomials with this support. We'll have something here, a coefficient A0, A1, A2 plus y times B0 plus B1x. This is the form of our coefficients. And then in this case, this is a case of a Cayley configuration. We have these two parallel configurations. It coincides with the resultant of these two polynomials. And then to compute the resultant, again, we can solve here x equals minus b0 over b1. We replace here, we clear the denominator, and we get the discriminant. This is the discriminant. This is the condition under which a polynomial with these coefficients is the closure of the condition under which it will have a singular point xy in the torus with non-zero coordinates. So we have f, we have the discriminant, and then we consider the singular locus, but the schematic singular locus. So what we do is we consider the ideal generated by the partials of this discriminant. Okay? These are the partials. And this ideal is not radical. We see it immediately. In fact, the radical is just generated by B0, B1. And the radical square is contained in the ideal. In fact, in this case, the mixed discriminant, so we would like also to compute the iterated discriminant as the mixed discriminant in an iterated way. But the mixed discriminant has degree 8, while the iterated discriminant has degree 12. And there is another factor, which is something squared. And this other factor is the CHOW form corresponding to the singular locus, where if F0 has coefficients small a and b, and F1 has coefficients capital A, capital B, then the CHOW form is equal to this, is correspond to this being the radical. So we get, if we compute the iterated discriminant, we get what we want times this square. So what is, I would like to recall the definition of CHOW form for you for a second. So if we have an irreducible and reduced projective variety of codimension S, then if we consider linear subspaces of dimension, projective dimension S minus 1, generically they won't intersect Y, but then we consider all those linear spaces of this dimension that do intersect. It happens that this is a reducible variety, and it has codimension 1 in the Grassmannian, and its defining polynomial is the CHOW form. So this CHOW form will vanish on all those linear spaces which are not supposed to intersect by dimensional reasons, but which do intersect our variety Y in these exceptional intersections. Sorry. And so this is, I have another example. Yes. So this is also an easy example. So we are again in one variable. The exponents are 0, 1, 2, 3. So this is the family of cubic polynomials in one variable. So given two cubic polynomials depending on a variable x, their mixed discriminant equals the discriminant of the Cayley configuration. The Cayley configuration is, again, you put 0, 1, 2, 3 at level 0 and 0, 1, 2, 3 at level 1. So we have these two parallel strands. This is the support of the Cayley configuration. And then we consider polynomial P0 of x plus lambda P1 of x with lambda a new variable. And the associated discriminant equals the resultant of these two polynomials, as we had a second ago, and it has degree 6. So the iterated discriminant will have degree 6. And so this is the mixed discriminant, but the mixed discriminant is going to have degree 6. And the iterated discriminant, if we consider dA of this, and then we take the discriminant of the degree 4 polynomial that we get something of degree 24. So we have the difference is 18, and this 18 comes from a factor of degree 6 raised to the 3rd power. And this factor is given by the CHOW form of the singular locus, and the singular locus of the discriminant corresponds to degree 3 polynomials with a triple root. This is the first instance of a degenerate multiple root. Okay, so let me give you a quick overview of our results. So we show that in the non-defective case, non-defective means that the dual variety has codimension 1, so we do have a discriminant equation. The mixed discriminant is always, this is the object that we would like to compute. This takes care of non-transverse intersections. Is always an irreducible factor of the iterated discriminant. And it's very nice, this comes from something which is called biduality, which essentially says the following. If you have a regular point in the dual variety, then a way, so you know that the corresponding hyperplane will intersect XA non-transversally, and in general, this will happen at a single point, and this point can be recovered from the gradient of the discriminant at this point. So we can recover the point of intersection generically via the gradient of the discriminant. This is very, very beautiful, and this holds in characteristic 0. When A is non-defective, we're going to call Sing XA dual the subscheme defined by the ideal generated by the partial derivatives. And we show, in fact, that this easiest way of computing this iterated discriminant can have other irreducible factors, which are given by the CHOW forms of higher dimensional irreducible components of the singular locus. We investigate when these other irreducible factors do not occur in two contexts that I will describe. And the general answer is related to the difficult problem of determining the codimension and the components of the singular locus of the dual variety, which are in general pretty unknown. But what is interesting, given that this is always divides, if this doesn't vanish, then the mixed discriminant does not vanish. So if this is non-zero, we get a certificate that the intersection is smooth. So even if we have other factors, we can use it to test smoothness of intersection. Okay, so this is a more precise statement. So again, we fix supports a set A, define a number of points, and a number R, which is between 0 and the dimension of this variety. Again, this is the affine dimension of the configuration of points. And we are going to call C the codimension of the singular locus of the dual variety inside the dual variety. So in general, the dual variety, we are assuming this is a hypersurface. If you have a hypersurface, in general, you expect that it will be smooth, or maybe it will have singularities, but maybe isolated singularities. But discriminants are not generic hypersurfaces, and in general, they do have singularities in codimension 1. They are way non-generic hypersurfaces, these dual varieties. So we are going to call C the codimension of the singular locus of the dual variety inside the dual variety. Then what we prove is that the mixed discriminant divides the iterated discriminant. If the codimension is bigger than R, then we have equality. And we can compute what we want, the mixed discriminant, using the iterated discriminant. If they are equal, then we get all these factors coming from the CHOW forms of the reducible components of the singular locus of codimension R. And we prove that these multiplicities are at least 2. And if the codimension is smaller, then this is identically equal to 0. So in fact, I gave you a naive definition of iterated discriminant. There is a geometric definition that we need to use in the proofs, but I am not giving you this definition. And the proof, to our surprise, when we started proving it, we needed to use everything we knew for many, many years about discriminants. So all the details I ever knew, we need to use in the proof. Okay, so when can we expect that we exactly compute mixed discriminant from the iterated? When the codimension of the singular locus is bigger than R. Okay, so at least to have a chance to put R equal to 1, we need that the codimension is at least 2. Okay, so the question is, for which configurations do the mixed discriminant and the iterated discriminant coincide? Or when is it that the codimension is bigger than R, or at least it's bigger than 1? So we have space to put at least R equal to 1. Well, in fact, previous work showed that it was for 2 quadrics in any number of variables. This is a very nice paper by Giorgio Ottaviani. It works for bilinear forms in any number of variables, or trilinear forms in 3 variables. This is the only known case of degree 3. And this is the only ones for hyperdeterminants. These are multilinear polynomials. And this was proved by Weiman and Zelevinsky in a nice article in 96, I think it's Annales de l'Institut Fourier, if I am not wrong. And in fact, these hyperdeterminants are the equation of the duals of Segre varieties. And what they do is they do a detailed study of the singularities of these hyperdeterminants. And they show that there could be many components of different types, more than what one could imagine. So it's not that the singular locus is reducible in general, or even I will go back to this, which are the components in a way. So what they prove is the only cases for which a mixed discriminant of the Segre embedding of a product of projective spaces can be computed as an I with degree 1s, with each one is embedded with O1, can be computed as an iterated discriminant are the Segre embeddings of the following varieties, either sorry, it doesn't want to work when I want, either just we have a square matrix. So if we have a square matrix, in the space of square matrices, the discriminant is a singular ones is when the determinant is equal to 0. So we have a matrix of size m. So determinant equal to 0 means that the rank is not m, which is the next level of singularity. Okay, it's not m, but it is m minus 1. So the singular locus of this discriminant is when all the minors of size m minus 1 vanishes, but there are many of them. This is why we get high codimension in the singular locus of the this determinant in this case. And here, this is the case that I told you there. It corresponds to P1 times P1 times P1. So what we proved, so they consider, we consider more generally Seger-Veronese embeddings, and then we consider here line bundles of higher degree. So we consider Seger-Veronese varieties given by these products. So we admit not only a product of several copies, but also higher degrees. And we have a complete result when all the degrees are at least 2. So the only case for which a mixed discriminant can be computed as an iterated discriminant is only when we have 2 quadrics in n variables. This was the case already studied by Ottaviani, but we give a completely different proof, and we prove that this is the only case that could happen. So for any, you choose any L, any D's at least 2, and this is the only possible case. And our proof is quite complicated combinatorially. This is art of Ralph Morrison. And we compare the degrees, and we conjecture that there are no other cases. So the missing cases are when some of the i's are equal to 1 and some are not. But we don't have a complete proof in this case, but we conjecture that essentially this is all that exists. And this is easy. We use the degrees, and the degree of the iterated discriminant in this case is computed with this way. So we can see that the degree of the iterated discriminant and the mixed discriminant scale differently as the degree go to infinity, but then you need to know when the first disagreement is found. Okay, so another case in which we prove that there is equality is now we have a smooth lattice polygon. What's a smooth lattice polygon? Well, lattice polygon means that the vertices are lattice point integer points, and smooth means that the first integer vectors for each vertex, this first integer vectors in the direction of the adjacent edges, you take the first vector you find in this direction, that the determinant has to be 1 or plus 1 or minus 1. So then these vectors are a basis of Z2. So this is smooth, and A, we take as A all the lattice points of a smooth lattice polygon in the plane. And then in this case, we did prove when is it that the mixed discriminant can be computed by an iteration, and via the iterated discriminant, which is equivalent to say that the associated discriminant has singularities for dimension bigger than 1. And there are only 2 cases, the cases that we already have. Either the polygon is the 2 triangle, so we get polynomials of degree, homogeneous polynomial of degree 2, or the bilinear polynomial, so the square. There are no other cases. Sorry, I want to sneeze, but I cannot. Okay, and in fact, there's not much work done in this direction. We found this, these are the references that we found. There is a very nice article by Bernard Morin and Laurent Busset in Mathematics of Computation 2009. What they do, they study the dehomogenization of homogeneous polynomials in 3 variables. So they have polynomials in 2 variables, and they compute an iteration of discriminants, each one in 1 variable. They iterate discriminants in 1 variable, and they get complete factorization. They get a complete factorization, and they get the exponents, which are either 2 or 3, and I will tell this in 2 items after this. But the methods they use cannot be used in the sparse case. We cannot do a linear change of coordinates. We cannot increment. So the methods that they use cannot be generalized. There is also a paper by produced at the same time. This is Journal of Symbolic Computation, also 2009, by Daniel Lazare and McCallum. It's called iterated discriminants. But again, they have polynomials depending on many variables, but they choose 2 variables, and then they iterate the discriminant, univariate discriminant with respect to these 2 variables. And they prove some nice general results. And then if we looking at our examples and some that we computed that I didn't put in the slides, and the results by Bernard and Rambuset, we conjecture that in fact we prove that the exponents are always at least 2, but it's more or less clear that the conjecture is that the exponent should be 2 if we get a component of the double point locus. These are those P for which the intersection is tangent at 2 non-degenerate distinct points, while it has to be 3 if it's a component of the cusp locus, which correspond to those P for which there is a multiple root which is degenerate, where the Hessian also vanishes. So this is essentially the only 2 types of components of codimension 1 that could occur. This comes from a result by Katz again. But the question is, okay, when is it that these components are present? Well, there is this thorough study for hyperdeterminants by Weiman and Selevinsky. And there is a nice article which addresses a very particular case. This is by Nikitin, he's a student of Alex Esterov. And here, the original DA is not that we take then the discriminant, but the original DA is a mixed discriminant of 2 planar configurations. And it was posted before, but the last version is from last October. And he studied this particular case, and already this case is quite involved. And I haven't seen any other study of describing singularities of discriminants in general. So summarizing, so the mixed discriminant divides the iterated discriminant, but other factors occur for 2 or more polynomials with the same support A in n variables, unless the singular locus of the discriminant variety has codimension bigger than 1 in the discriminant variety. We identified these factors and we studied when the iterated procedure gives the expected result without any other factors, but only in a few cases. Because in general, discriminant hypersurface have in almost all cases singularities in codimension 1. But anyway, as I said, iterated discriminant can be used to partially describe these singularities and can be used as a certificate for a smooth intersection. And this is all, and I thank you very much for your attention.
Thank you, Alicia. You actually finished quite early. Yeah. Okay, thank you very much. Thanks, Alicia, for a very nice talk. Any questions? Yes, question in the chat. Let me read. Can discriminants be computed in positive characteristic?
Yes, they can be described in computed in positive characteristic for sure, but we essentially use biduality, and biduality has trouble in positive characteristic.
So is it the only abstraction to generalize for positive characteristic, or there are others?
I really don't know, because we're using derivatives all the time. I cannot tell you. One has to be very careful to check the proofs and be sure that everything is working. Somehow we are misregarding integer factors. We are not careful about this, so I don't know.
I see. Thank you, Cesar, for nice question. Thank you, Alicia. And I have general questions. So, do I understand correctly that the nature, in some sense, of this research is a bit like applies mostly to toric varieties? Yeah.
Okay, we did a study for toric varieties. You could try to generalize this more in general. So the question is, you have a different families, polynomials in different families that need not be coming from a toric family, not fixing the exponents, and you would like to understand the non-transverse intersections and try to, okay, of course, you can define, so in fact, if you go to Gelf and Kapranos-Levinsky, there is the notion of X-discriminant of a variety. You can define the X-discriminant, and you also can define the mixed discriminant, which is essentially comes from the Cayley. You can define the mixed discriminant again for any X, and some of the results I'm sure that will hold, but I don't know which detail you can. Yeah, of course, you can go far beyond the Tori case.
Okay, thank you. Any other questions? Okay, another question. Are there some connection between iterated discriminants and tropical discriminants?
Of course, you could try to tropicalize this construction that we didn't do. So we started trying to compute the mixed discriminant using some tropical tools, and then we got terrible information. Even for the case of two quadrics in 3 dimensions, we got we got some tropical information, but it was too huge. It was impossible to do something for us to do something interesting with this. And then we decided to instead to look for what were they doing geometrically, and how can we generalize this. We were intrigued why they were using this and why this worked, but I don't know.
Okay, very good. Thank you. Thank you.
You're welcome.
Any other questions? Please type in the chat, or you can just ask. Okay. Yes, another. Okay. There's comments. No. Okay. If there are no more questions to Alicia, let's thank Alicia again. Thank you very much.
You're welcome.
Thanks. Okay. Let me stop recording. Okay.